Hello again. In this lecture, we'll explore what concatenating is and how to use the relevant NumPy function to do it. Let's begin. We'll start by loading and displaying the dataset we will examine, lending company numeric. By now, you've already seen how to do this multiple times, so we'll jump right into the definitions. In a nutshell, concatenating is the act of linking together objects in a chain. In NumPy, it's like stacking, because we're creating a new larger array by merging existing smaller arrays along a given axis. The along a given axis part is crucial because the inputs and the outputs of the concatenate function always have the same number of dimensions. For example, if we concatenate two columns, the result won't be a 2D array with two columns, but rather a single longer column. This is best understood with an example. So let's concatenate the first two rows of lending company data numeric. The syntax of NP concatenate is very similar to NP stack. All we need to do is write the name of the function and within a tuple, pass the arrays we want to link. The output is a 1D array, which begins with all the values of the first row, before attaching to them the individual elements of the second row. As we mentioned above, this differs from stacking, because even though we're storing the values of both arrays, we're still confined to one dimension. Now, let's see how concatenating works for 2D arrays. To do so, we need a second dataset. This time, we'll import the NaN version and fill out its missing values. You've already seen how to load it. Store the means, create a filler, plug in that filler into any empty spots, and then switch those with the appropriate means for every column. If we plug in the two datasets, lending company data numeric and lending company data numeric NaN, we'll see a familiar sight. The output contains 6 columns and looks identical to the output of the hstack function from our last lecture. This is because we've concatenated the second dataset at the bottom of the first. We can verify this by looking at the third row from the bottom. It contains the value 2250.25, which was the filler for the first column. To make sure we're not misinterpreting the output, we can always check the shape of the concatenated array. The result reads 2086 by 6, which lines up with our assumption, as both lending company data numeric and lending company data numeric NaN are 1043 by 6 matrices. Because the inputs are two-dimensional, we now have two axes to choose from when concatenating. Let's see what happens when we set axis equal to 1. Judging by the ... in every row, it's safe to say the output consists of more than 6 columns. In fact, since we're concatenating the two arrays side by side, we can assume the new array has 12 columns, 6 from the lending company data numeric, and another 6 from lending company data numeric NaN. Instead of speculating, we can once again check the shape attribute to verify this assumption. We obtained 1043 by 12, just as expected. Fantastic! Now, if we set the axis to 2, we'll get an error message, because the inputs only have 2 dimensions. However, let's once again create two 3D arrays and see how the outputs match up. We'll quickly call concatenate and set the axis equal to 0. Then we'll call vstack on a new line and we'll get the exact same output. After that, we'll set the axis to 1 and change vstack to hstack. Once again, the two are identical. Finally, we'll set the axis equal to 2 before calling dstack. For the third time running, we get identical outputs, so concatenate can replicate the outputs of these 3 stacking functions. Overall, it seems that concatenate works exactly like vstack, hstack, and dstack, depending on the inputs and axis arguments. Hence, it's a very flexible function. All right, one last topic we want to touch on is concatenating inputs of different shapes. If the two arrays are one-dimensional, They don't need to hold the same number of elements since the output is in the first dimension as well. We can quickly try this by concatenating the first row and first column of the lending company data numeric. As we can see, there is no issue here. So, unlike stacking, concatenating in 1D does not require the inputs to have the same shape. Let's see what happens if the two inputs are of different dimensions. How can we do that? It's simple. Just delete the indexing from one of the input arrays and rerun the cell. We get a value error explaining concatenating among different dimensions is prohibited. However, if we have arrays of the same dimensions but different shapes, we can still concatenate them, but only if their dimensions match for the axis we're concatenating along. Hence, if we remove a row, we can still concatenate vertically because the number of columns is identical. But if we remove a column, we get another value error explaining the mismatch in dimensions. Of course, in cases like this, we can just switch the axis argument to 1 to link the two datasets horizontally. Fantastic! Now that you've learned how to concatenate data in NumPy, we're ready to learn about a different aspect of preprocessing. In the next lecture, we'll examine how to discover the unique values in a dataset. Thanks for watching!